Assalamualaikum and salam sejahtera. Welcome to our presentation. We are from Group F, which consists of myself. So my name is Muhammad Zafarhan bin Muhammad Ashraf Fizi, E24A3141.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Khairi bin Ahmad Zamri from Group F. Matrix number is E24A3167.
Hi, my name is Muhammad Daniel Irwan and my matric number E24A3181.
Hi, my name is Muhammad Amin bin Ibrawi. My matric number is E24A3246.
Hi, my name is Pravi and my matrix number is E24A333.
We will be presenting on geochemical processes in soil, rocks and water. Alright, I will start with the introduction of geochemical processes in soil, rock and water. Basically, this is my content, which is I will present about introduction, what is geochemistry, why is geochemistry important, Earth geochemical system, presentation roadmap, and real-world application of chemistry. Explore how chemical processes shape and connect the earth, soil, rocks, and water. Geochemistry helps us understand our planet's system and their impact on the environment and human life. First, let's define what geochemistry actually is. It's the study of the chemical composition of the earth and how does chemicals change over time. This includes processes happening in soil, rock, and water, and even living organisms. Geochemistry brings together chemistry, geology, and environmental science to explain how elements move and interact in the natural world. Imagine it like the Earth's own chemistry lab, constantly running reactions that shape our environment. So, why should we care about geochemistry? First, it helps us find and manage natural resources like minerals, oil, and groundwater. It also plays a big role in monitoring pollution. For example, detecting heavy metals in river or change in soil pH. In agriculture, geochemical analysis helps improve soil health and crop yields by understanding nutrient levels. And finally, it supports climate studies by tracking carbon and other elements that affect the atmosphere. So, geochemistry touches many areas that impact both people and the planet. Now, let's take a look at how Earth system interact geochemically. We mainly focus on three components, which is soil, rocks, and water. Despite constantly changing element through natural processes. For example, rainwater can break down rocks and carry minerals into the soil, or elements in the soil can dissolve into rivers and travel to the ocean. This interaction create complex but fascinating cycles that maintain us balance. Here's how our presentation will be organized. We'll start with geochemical processes in soil, how nutrients move, what affects soil composition, and more. Then we'll explore geochemical change in rocks, such as mineral formatting and weathering. After that, we'll cover water system, including rivers, groundwater, and how chemistry change in aquatic environment. Uh, we will wrap we will wrap up with visuals, key takeaways, and how all these systems are connected. Geochemistry is not just theory; it has many practical uses. In agriculture, it helps determine which fertilizers are needed by testing the soil. In mining, geochemical surveys are used to find valuable mineral deposits. Environmental scientists use it to monitor pollution in river or groundwater, and finally, it plays a critical role in climate research, helping scientists understand carbon cycles and greenhouse gases. So you can see geochemistry is a powerful tool for solving real world problems.
Assalamualaikum and good morning everyone. Today I will talk about my presentation about geochemical process in soil. So basically my name is Muhammad Daniel Irwan Shah and you can call me Iwan. So my metric number is E24A3181 and I am student geoscience first year. Today I'm going to talk about something that happening right under our feet. So it's a geochemical process in soil. These are natural chemical change that help from soil move to nutrient and keep ecosystem healthy. Uh, the content I will explain for my part is introduction, watering of mineral, adsorption and disruption, redox reaction, and organic matter decomposition. Okay, let's move to my first introduction about geochemical process in soil. First thing first, for introduction, geochemical process are chemical reaction that happen in soil. They involve things like water, mineral, gases, and organic matter. This reaction help break down rock and release nutrient and even clean up pollution. Okay, go to first like a watering of a mineral. Okay, watering of a mineral have two type. They have a big process in watering. They have a two type. The first one is physical watering, and the second one is a chemical watering. Okay, I explain first about physical watering. Okay, physical watering is rock break into a smaller pieces from wind, water, or temperature, and the process involved in physical watering like thermal expansion and concentration and a growth and root grow in a rock crack. That is a physical watering. How about chemical watering? Okay, chemical watering, water and acid dissolve or change a mineral into thing like a clay, and the process involved is like hydrolysis, oxidation, carbonation, and dissolution. This is how soil is made from rock over time. So let's to next slide. Okay, the next slide is adsorption and disruption. Okay, adsorption and disruption are the key in geochemical process in soil. Why? Because they control how substance like nutrient, uh, contaminants, and metal interact with a soil particle. So have a two, eruption and disruption. Okay, eruption is when nutrient or chemical stick to soil particle, and then disruption is when they are released back into the water. This is effect whether nutrient stay in soil or get washed away. Okay, the next slide I will explain about precipitation and dissolution. Two, have a two. Okay, precipitation and dissolution are two fundamental geochemical process in soil that control the formation and breakdown of a mineral. Okay, element become immobile, may reduce nutrient availability or from mineral coating in soil particle. Okay, dissolution, the process where dissolved ion in soil water react to from solid mineral compound which settle out of a solution. That is happen when mineral dissolve in water precipitation. And the process where solid mineral dissolve into soil water, so the breaking down is a breaking down into their constituent ion. This is when they are formed solid again. Okay, for example, calcium carbonate can dissolve in acid water or from solid in basic basic soil. And we move to next slide. The next slide I will explain about redox reaction. Okay, redox reaction. Redox stand for reduction and oxidation. Okay, two type, reduction and oxidation. Okay, I will explain about oxidation first. Oxidations mean losing electron, often involve addition of oxygen or loss of hydrogen to oxygen or hydrogen. It means loss. Reduction is mean gaining electron, often involve removal of oxygen or gain of hydrogen. Same like a same. So, uh, oxidation and reduction is mean losing and gaining, and you can easy remind about that. So, in soil, redox reaction change the chemical form of element like iron, magnesium, nitrogen, and sulfur. This change affect their color, mobility, and availability to plants. Okay, you understand that? Uh, the last one, I will explain about organic matter decomposition. Okay, organic matter decomposition when plant and animals die. Everyone will die. Everyone will who life will die. So like a plant and animal, and microbes break them down. This process release nutrient like nitrogen and phosphorus into the soil. It's a produce acid that help with watering and chemical change. So that's all for me. That's for my explanation about my part. So I will move to the next part and the next member to explain.
Assalamualaikum warahmatullahi wabarakatuh. Today I will present to you all about the geochemical process in rocks. My name is Muhammad Khairi bin Ahmad Zamri. Proceed with the first point. First of all, My contents is introductions, weathering in geochem rocks, geochem in all type of rocks, absorption and desorption, geochemical application, dissolution, and precipitation. First of all, the introduction is about geochemical. Geochemistry is the study of the chemical composition of the earth and its rocks, minerals, and fluids. When we talk about geochemical properties in rocks, we are referring to the chemical elements and isotopes present in the rock and what they tell us about the rock's origin, history, and environment. For the major elements, these include elements like silica, aluminium, ferrum, magnesium, calcium, natrium. They make up most of the rock's mass. Example, high silica content usually indicates a felsic rock like granite. The trace elements present in small amounts, ppm or ppb. This include elements like zinc and nitrogen. Useful for fingerprinting rock sources and processes like partial melting or traditional crystallization. And the second is chemical weathering. Chemical weathering is the change the chemical composition of minerals and rocks through reactions with water, oxygen, acids. The main process is the first hydrolysis, reaction with water, example feldspar, into the clay minerals. The second one, oxidation, reaction with oxygen, example iron minerals into rust. The third one is dissolution. Minerals dissolve in water, for example calcite in limestone dissolve in rainwater. And lastly, carbonation. Carbonation is CO2, carbon dioxide, plus water forms carbonic acid in equals to dissolved minerals like calcite. Next, physical or mechanical weathering breaks rocks into smaller pieces without changing their chemical composition. For example, frost wedging. Frost wedging is meant by water freezes in cracks, expands and breaks rock apart. The second one is thermal expansion. Repeat heating and cooling causes rock to crack. The third one is abrasion. The abrasion is mean wine, water, or ice grinds rocks down. And lastly, pressure release, exfoliation, expansion of rock after overlaying pressure is removed. Okay, next, factors of affecting weathering rate. We have 4 factors here. The first factor is rock type. The effect hard rocks, example granite, weather is lower than soft ones. The second factor is climate. The effect is warm, wet climates enhance chemical weathering. Cool or dry favor physical. The third factor is surface area. The effect is more area equals to faster weathering. And last factor is time. This effect, longer exposure equals to more weathering. And next, biological weathering. Biological weathering is living organisms contribute to rock breakdown both physically and chemically. For example, plant roots grow into cracks and pry rocks apart. Next, the second one is lesions and microbes secrete acids that chemically degrade the minerals. Okay, next I will talk about geochemistry in all type of rocks. We have three type of rocks. First one is igneous rock, second sedimentary rocks, and lastly metamorphic rocks. I will start over the igneous rocks. Igneous rocks is geochemistry in igneous rocks involves studying the chemical elements present to understand how the rocks form, evolve, and what process shape them. Second one is sedimentary rocks. Geochemistry in sedimentary rocks involves studying the chemical composition of these rocks to understand their origin. Weathering processes, source material, depositional environment, and post-depositional change. And lastly, metamorphic rocks. Geochemistry in metamorphic rocks focuses on how the chemical composition of rocks changes or remains stable during the metamorphism, which is the transformation of the rocks under heat, pressure, and fluids. Geochemical analysis helps understand the protolith, original rock, metamorphic grade, fluid interaction, and tectonic setting. Next, I will go through to the absorption part. Absorption in rock geochemistry are crucial surface processes that affect the mobility, concentration, and environmental behavior of elements and compounds, especially trace metals, nutrients, and contaminants. First of all, adsorption in rocks. Definition of adsorption in rocks is the process where dissolved ions or molecules in fluids stick to the surface of minerals in rocks. Where it happens, for example, the clay minerals like kyanite and iron and magnesite oxide like MnO2, carbonates, and organic matter coatings on grains. Next, desorption. A common adsorbed substance is the first one is heavy metal, second nutrients, and the third radionuclides. The geochemical importance for this part is it will control your element mobility in groundwater and surface waters, affects weathering processes and element cycling, plays a major role in contaminant transport in rock aquifers. So the desorption in the rocks is meant by the release of absorbed ions or molecules back into the solution, typically due to change in the environmental conditions. It was triggered by pH change, redox change, increased ionic strength, and competition from other ions. Okay. Now we will talk about igneous rock structure. Igneous rock structure is divided by common geochemical, like diagrams and like application in petrology. Next, a geochemical application in sedimentary rocks. We have 5 purpose on this application. The first one is provenance, and second weathering intensity, the third redox condition, and the fourth dynamic change. Lastly, paleoclimate reconstruction. And the application of the geochemistry in metamorphic rocks. We have also 5 purpose. The first is identify protoliths. Second, determine metamorphic grade. Third, detect fluid rock interaction. Fourth, metamorphic reaction and PT packs. And lastly, date metamorphic events. So now we'll talk about dissolution. Dissolution refers to the process in which a solid mineral or rock dissolves in a solvent, typically water, resulting in the mineral's ions or molecules being released into the solution. The first one is mechanism. Mechanism: the dissolution of the minerals occurs when the mineral interacts with water or other solvents, causing the bonds between atoms or ions in the mineral to break. Water molecules surround and separate the ions of the mineral, leading to the mineral's dissolution. For example, the dissolution of calcite CaCO2, a common mineral in limestone. Factors of affecting the dissolution is the temperature, pressure, pH of the solution, and the chemical composition of the solvent, and can affect the rate.
Well, hello everyone. My name is Praveen, and today I'll be presenting to you on my topic, which is geochemical processes in water. So, as we know, geochemical processes in water refers to natural chemical interactions between water and the Earth's materials. These processes are essential to understanding water quality, environmental changes, and even climate systems. Let's begin our journey by looking at what these processes are and what are they actually about. Water. When you hear the word water, it may seem simple. As we know, its characteristics are like clear, tasteless, and odorless. But geochemically, it's very active. It constantly interacts with minerals, gases, and organic matter in its environment. These interactions alter its chemical composition over time, influencing everything from the taste of our drinking water to the formation of cave systems and salt flats. Okay, we can categorize these interactions into a few, as they include weathering, dissolution and precipitation, ion exchange and absorption, redox reactions, and many more. So let me explain one by one. So what can we categorize as weathering? So weathering is where rocks break down due to chemical reactions with water. Next up, when you hear the word dissolution and precipitation, we think about when minerals either dissolve into water or form solids again. Next up, we have ion exchange and adsorption. So what can we summarize from that? It means that those are processes that change water's chemistry by swapping or trapping ions. Next up is redox reactions, where chemical species gain or lose electrons, often transforming into new substances. And there are a few more processes which will be presented by my friend Farhan. Now let's take a closer look at each process, starting with weathering. We carry on the first process, which is called chemical weathering. So what can we conclude from chemical weathering? Chemical weathering basically is about breakdown of rocks by acidic water. For example, calcite dissolution releasing calcium and bicarbonate ions. There's also a cycle called carbonate silicate cycle, where it's a weathering role in long-term carbon dioxide regulation. As I said before, weathering is the first major process to understand in geochemical properties in water. It begins when rainwater slightly acidic from dissolved carbon dioxide reacts with water. This is called chemical weathering. Another type of silicate weathering, which occurs more slowly but has an important role in regulating the Earth's climate. It consumes carbon dioxide over long periods, helping balance the greenhouse effect. So weathering basically summarizes two things. First thing, it releases ions like calcium, sodium, potassium, and silica. And second thing, it alters rock structures. And not to forget, it also contributes to global carbon cycling. As you can see in the visualization provided of the carbonate silicate cycle. This is the example of silicate weathering where silicate minerals in rocks break down more slowly, helping regulate the Earth's carbon dioxide levels over long time scales. As you can see the shown reaction below, that is the proper reaction for the carbonate silicate cycle. So through that, we could summarize that weathering is a starting point and also the most important part of the dissolved materials we find in rivers and groundwater. Next up, we have dissolution and precipitation, which are two opposite but complementary processes. So what dissolution? What can we refer from that? Dissolution happens when minerals dissolve in water. For example, in nature, when groundwater flows through salt-rich rocks, these ions are released, increasing the water's salinity. What about precipitation? However, precipitation, on the other hand, occurs when water becomes saturated with ions, meaning it holds more than it can keep dissolved. The excessive ions then form solid minerals that fall out of the solution. Like for example, when water evaporates in a shallow lake, dissolved ions become more concentrated. Eventually, minerals like gypsum or halite begin to crystallize out, forming evaporites. So there are two processes that are undergone during dissolution and precipitation. First of all, the first process is about controlling the concentration of dissolved substances. Second, about influencing the formation of mineral deposits. And lastly, to add on to the both of the two processes mentioned just now, we have those are the key to understanding salinity and scaling in pipes or wells. So as you can see in the visualization provided of dissolution and precipitation process, you can see, and the definition is given below. So precipitation is the process of a compound coming out of the solution. It is the opposite of dissolution or solvation. Meanwhile, in dissolution, the solute particles separate from each other and are surrounded by solvent molecules. In precipitation, the solute particles find each other and form a solid together. Next up, let's look at ion exchange. So when you heard about ion exchange, it might look a little bit complex, but it is a very impactful geochemical process in water. So basically, ion exchange occurs when ions dissolved in water are swapped with ions that are attached to solid surfaces such as clay, minerals, or organic matter. Let me give you an example. When groundwater flows through clay-rich sediments, sodium ions attached to the clay might be exchanged for calcium ions in the water. As a result, the water becomes softer or harder, depending on the exchange. So this process basically affects water hardness, which is important for plumbing and taste, influences salinity, and most importantly, it plays a vital role in contaminant transport, especially for metals like lead or arsenic. So in order to make it relevant to our environment, so in environmental remediation, ion exchange is used to clean up contaminated water, replacing harmful ions with safer ones. So although it's not always visible, ion exchange significantly modifies water chemistry, especially in soils and aquifers. As you can see in the visualization given of the diagram of ion exchange mechanism, where contaminated water is undergone certain ion exchange process to produce treated water. As I explained previously before, this process affects water hardness and salinity and plays a vital role in softening or contaminating water, especially in areas with lots of clays or ancient marine sediments. Ion exchange is particularly important in aquifers and helps explain why water from different geological layers can have very different chemical signatures. So next up, we have a certain process which is closely related to ion exchange, and this process is called process of adsorption and desorption. So adsorption, what can we refer from that? Adsorption is when ions or molecules stick to the surfaces of minerals or organic matter. Meanwhile, desorption is the reverse of adsorption. That is when they are released back into the water. So what are released back into the water? The ions or molecules from the surfaces are released back into the water. So why is it important? Because it is the key mechanism for filtering contaminants. For example, arsenic may adsorb onto iron oxide minerals in soils. Phosphate may bind into aluminum hydroxides, and even some viruses can be absorbed onto clay particles. So what's the main function of adsorption and desorption process? So it plays a role in trapping or releasing contaminants like heavy metals. To conclude more about that, I would like to say adsorption basically removes substances from water, which could be removing temporarily or maybe also permanently. Meanwhile, desorption can release pollutants under the right conditions. So it would only release pollutants under certain circumstances. Following up, we have one of the most dynamic geochemical processes in water, which is redox reactions. To be shortified, to be short and sweet, we will call it as oxidation and reduction process. Basically, redox reaction, which is oxidation and reduction, involve the transfer of electrons between chemical species, which often changes their form and reactivity. Here's an example. Like iron in groundwater often exists as ferrum 2+, in a soluble form. But when it encounters oxygen, it oxidizes into ferrum 3+, forming insoluble iron oxides. So those reddish or orange particles you sometimes see in streams or well water might be them. Not forgetting the benefits that are formed from redox reaction. So it is important in nutrient cycling and also contaminant mobility. Redox reaction is really important, especially in low oxygen environments like groundwater aquifers, wetlands, and also sediments at the bottom of lakes. This is because in these places there are lack of oxygen, so oxidation is needed to make these places appear or attempt to look more environmental friendly. Not forgetting, redox processes are also heavily influenced by microbial activity, which we'll touch on in later slides. They are crucial for nutrient cycling, contaminant breakdown, and controlling water quality. So about the microbial activity, it will be presented by my friend Farhan later on. As you can see in the illustration given of the redox reaction diagram, which is the oxidation and reduction diagram. So the diagram visually represents the electron transfer that occurs between reactants in a chemical reaction. It shows which reactants are oxidized. Oxidized means it loses electrons. Meanwhile, reduced means it gains electrons. And the overall change in oxidation numbers. For example, I said like previous before, iron 2, which is soluble, is undergoes oxidation and oxidized, forming rust-like particles that settle out of water. So ferrum 2+, which is oxidized into ferrum 3+. And next up is complexation, a process where dissolved ions from complexes with other molecules or ions in water. For example, a metal like copper Cu2+ might bind to humic substances, which are large organic molecules in natural water. This forms a copper-humic complex, which stays dissolved longer and behaves differently from free copper ions. So basically, why does this matter? It matters a lot because in complexes often increase solubility of metals. They can either protect aquatic life from toxicity or enhance transport of contaminants. Composition affects nutrient availability, especially for tracing metals like zinc and iron. This is a key process in surface waters, wetlands, and areas rich in organic matter. Complexation can also play a role in water treatment, which is by keeping metals in a manageable form or making them harder to remove depending on the ligand. So even though it's happening at the molecular level, complexation has big consequences for both environmental and engineered water systems. As you can see in the illustration given, which is metal ligand complex. So as provided in the diagram, complexation is when metal ions in water from stable compounds or complexes with ligands like organic molecules or hydroxides. For instance, copper or lead may bind with natural organic matter, staying dissolved in water longer than they otherwise would. So that's all from me for my part. I would pass on to my friend Farhan.
Let's talk about evaporation and concentration. When the water evaporates from lakes or soil surfaces, especially in hot, dry environments, the remaining water becomes more concentrated with dissolved ions like sodium, calcium, and chloride. So as evaporation continues, these ions build up in the remaining water. Eventually, the solution becomes so saturated that minerals start to crystallize and settle out. This is how we get mineral-rich deposits, especially in areas where water cannot drain away. So the process leads to the formation of evaporate minerals like halite, which is essentially rock salt, and gypsum, which is used in things like plaster and drywall. This mineral form in layers and can be important indicators of ancient climates. Evaporation and concentration are especially important in arid environments and closed basins, since water cannot escape through rivers or stream. It only have it's only lived by evaporation, leading to intense build-up of salt over time. Uh, that's why that's why salt flats and dry lakes beds in deserts are often covered in white crusty layers of minerals. Here we can see a clear example of what happens during the evaporation process. This is salt flat, or an area where evaporate minerals have formed. As water gradually evaporates, it doesn't take the dissolved salts with it. Instead, the salt get left behind, becoming more concentrated. Over time, the ions begin to form visible crust or layer of minerals like halite, which we know as rock salt, and gypsum, used in construction materials. Um, this process doesn't just affect the chemistry on the water, it also significantly reduces the amount of available water, especially in closed basin like lakes and reservoirs where there's no outflow. The only way left is by evaporation, which makes these areas highly sensitive to climate change. Biogeochemical interaction processes where biology, chemistry, and geology all work together in natural system. One key player in this interaction is microorganism. They drive important geochemical reaction that shape the chemistry of soil and water. Micro Microbial activity can transform or break down chemical compounds. For example, in denitrification, bacteria convert nitrates in the soil or water into nitrogen gas, which is then released into the atmosphere. In another process called sulfate reduction, microbes convert sulfate into hydrogen sulfide under low oxygen condition. This reaction may sound simple, but they are crucial for maintaining environmental balance. Uh, this micro this microbial processes also play a major role in natural water purification and nutrient cycling. They help remove excess nutrients and contaminants from water, keeping ecosystem healthy. Without them, pollutants like nitrates or sulfates could build up and harm aquatic life. So, biogeochemical interaction are not just complex; they're essential for sustaining clean water and balanced environment. The diagram shows how microorganisms play a key role in driving geochemical reaction, especially in environments where oxygen is limited, such as sediments or wetland. Microbes thrive in these redox-sensitive areas can and help carry out important chemical change. For example, in denitrification, bacteria convert nitrate into nitrogen gas, which is released into the atmosphere. Another important process is sulfate reduction, where microbes turn sulfate into hydrogen sulfide, commonly found in waterlogged or anaerobic conditions. These microbial reactions are not just interesting, they are essential. They help purify water naturally, recycle nutrients, and even support systems like wastewater treatment plants and wetland restoration projects. Without microbiomediation, many ecosystems would struggle to maintain balance.
To conclude our presentation, we have explored how geochemical processes in soil, rocks, and water are fundamental to understanding the Earth's dynamic system. These processes, such as weathering, erosion, mineralization, dissolution, and precipitation, are constantly at work, transforming materials and influencing the natural environment around us. More than just academic concepts, these processes have real-world application. They help us managing agricultural productivity, preserving water quality, guiding mining activities, and addressing environmental pollution. By studying how chemical elements interact within soil, rocks, and water, we can better understand critical issues like soil fertility, groundwater contamination, and even the long-term impacts of human activities on ecosystem. Most importantly, understanding geochemistry supports our effort towards sustainability environment. It allows us to make informed decisions in resource management and environmental conservation, ensuring a balanced relationship between human needs and nature's capacity. In short, geochemical processes are not only vital for the planet's natural cycles, but are also key to solving environmental challenges and creating a more sustainability future for all of us. That's all from us. Thank you.